Hey everyone, welcome back to Robotics. I hope you guys are doing well. Today we have our 29th lecture on gradient descent. All right, so let's get started with a video. Now this is a video of autonomous racing. There are no humans on board these vehicles and no one's remotely controlling these cars. Instead, these vehicles are driving by themselves at high speeds on a professional race course. I like this video because it takes what we know about learning and control and then pushes that to the limit. I don't just want to learn how to drive, I want to learn how to drive as quickly as I can. So there's a combination of learning and optimization, and that combination is what we'll be talking about in today's lecture. I first want to introduce how learning connects to optimization, and then second, I want to provide the gradient descent algorithm and show its connection to robot learning. All right, so let's set the stage by just talking about control policies. Here's my control policy right here. Now this policy is going to input states and output actions. The states could include my joint positions, but it could also include things like camera images or LiDAR scans. The actions that I output could be joint torques, or they could be more general like desired positions. The idea is that my control policy, which again maps from states to actions, is parameterized by these weights W. And I don't know what the right weights are. The robot is going to try to learn the weights by itself in order to maximize its task performance. So maybe we can talk about these terms in a little bit more detail. First, let's talk about the control policy. The robot's controller is not fully specified. I want you to think about something like PD control, where the proportional and derivative gains are not given. We know we want to do PD control, but we want the robot to figure out the right gains for itself. So as a designer, we're going to provide this function and kind of give the robot the parameters it should use, and then the robot is going to tune those parameters itself in order to maximize its performance. One example could be a neural network. Another example could be linear regression, where here I've got a mapping from my states X to my actions U, and that policy is weighted by W right here. Okay, so I've got my control policy. Now, what's my goal here? Well, I've also got a loss function, and this is a performance function that's telling the robot what it should be optimizing for. And the robot is going to try to learn the parameters in order to minimize this loss function. So if I stick with my linear regression example, my loss function is the error between my predicted actions and the actual actions that I saw at training time. So again, this is my predicted, this is my actual, and I want to learn W in order to minimize this loss function so that the actions I predict match the actions that I saw. So it's up to us as designers to come up with what we want to have for the control policy and the loss function. We might also provide some training data to the robot, and then the robot's going to synthesize this training data, its control policy, and its loss function, and try to figure out what values of W it should have. Specifically, the robot tries to update W in order to minimize its loss across the training data. Now, you might notice that I keep using these optimization-like words. I'm talking about minimizing or maximizing, and that's because there's a very close connection between learning and optimization. And I want to show you that here as I talk about how robots update W in order to minimize their loss function. So one way we can do this is with an algorithm called gradient descent. And this is an optimization method. I can use it for many different purposes, but here I want to show you how you can use gradient descent to update W in order to minimize a loss function L. The first step here is I want to initialize W with my best guess of the correct weights. If I've got no clue, I can initialize W with noise, maybe drawn from a normal distribution, or I can initialize it with all zeros. But if I've got a good idea of what I want, I could use that with my first choice of W. And as you'll see, actually, this first choice can have a pretty big impact on your result. So if you know something, definitely leverage it here. The main loop is going to be in my next steps down here. And this is a loop where I update my guess of what my weights should be. And then I finally return my final guess of what I think these weights should be. The key equation's right here. And this is the equation that I'm using to update W. Now, this equation, it takes in my current guess of what I think W should be, and it updates it using the gradient. And specifically, I'm moving in the opposite direction of the gradient. Each time I go through this for loop, I should be getting a new value of W that has a lower loss than my previous value. Maybe it makes a bit more sense if I visualize the process. So let's say that I have a weight vector with two elements, W1 and W2. I'm plotting those on the X and Y axis. So here, this is my first guess what I thought the weight should be, W. These contour lines show different loss values. And the darker shades of gray correspond to higher loss. And then in the middle, I've got the lowest loss. At the beginning, I've got this high loss for my initial guess of W. Maybe it wasn't the best guess. I go down this gradient. I take a step of the gradient. I end up right here. I take another gradient step. I end up right here, and so on. So I'm updating my understanding of what the weights should be in order to try to minimize my loss function. All right, so there's also this parameter alpha, and I haven't really talked about it too much. Now, this is my learning rate. It's got to be something greater than 0. And you might think back to our previous lecture on numerical inverse kinematics. Similar to alpha in that lecture, my learning rate here governs how quickly I'm updating my weights, and I'm trying to quickly converge to the minimum value for this gradient descent. So increasing alpha is going to cause you to have fewer steps, but you might overshoot your goal. And so it's actually better to start off with lower values of alpha so you actually can converge to the minimum here. And so just like what we had for numerical inverse kinematics, we generally like to pick smaller values for alpha so we don't miss out on the optimal solution. Okay, so let's test our understanding. What happens if instead of having a minus sign right here, I put a plus sign so that I had this update rule? Maybe pause the video, think about it. You probably realize that this is not a good idea. If I did this, instead of having gradient descent, I would have gradient ascent. And I'd be finding the value of W that maximizes my loss function. That's probably the worst possible value of W I could have, so the sign really matters, and I want to make sure I'm going down that gradient and minimizing my loss. Okay, so what does gradient descent look like in practice, and how does it work? Again, let's think about this in a linear regression setting. Now, if you haven't watched our previous video, I encourage you to do so. In the last video, we talked a lot about linear regression, and I think this is going to make more sense if you've already seen that lecture. But just as a quick reminder, in linear regression, I have a control policy of the form U equals X transpose W, where X and W are k-length vectors, and U is a scalar. What I'm going to do is I'm going to collect a data set of labeled state action pairs. All my actions are going to be put into a d by 1 vector U, and all my training states are going to be put into a d by k matrix X. So again, I've got these states X, my actions U, and I've got my loss function down here. The goal is to try to learn some values of W such that my predicted actions match the actual actions I saw at training time. If I want to apply the gradient descent algorithm and find the right weights W, my first step is going to be to derive the gradient I need right here. So I want to find the gradient with respect to these weights. So maybe think about it for yourself, see if you can find that gradient. And I'm going through the process on the right side here. My first step is I take that norm squared and I write it out in a slightly different way. And this is just an easier way for me to take that gradient. I've got in parentheses xw minus u transpose times xw minus u. And again, equation 1 right here, this is just the same as what I have right here with this norm squared, just written in a more convenient way. Once I have it written out like this, now it's probably a bit easier for you to take the gradient. So I just take the gradient and end up with what I have in line 2, 2x transpose times xw minus u. This specific gradient isn't particularly important. It's not like I need you to memorize this equation, but what I wanted you to see was the process of finding the gradient. There are two general ways you can do this. What you saw right here, which is an analytical approach, but you can also use numerical approaches to estimate the gradient if you've got a very complex loss function. Okay, so I've got my gradient right here, and I'm just going to plug that into my gradient descent algorithm. So I've got my initial guess of W, great. At every step, I'll go down the gradient, great. And then I'll finally return whatever my final value is after going down that gradient for however many steps I choose. Here's what that could look like in MATLAB. So my first line, I've initialized my guess for W, and I've got no clue. I'm just guessing all zeros. I don't know what the right weights are. You can ignore the losses and plots for now. That's going to be for visualization. Let's skip down to the for loop. In this for loop, I've got 100 steps. So I'm going to do 100 steps of gradient descent. And this is the equation I'm using to update my values for W. Again, I've got my initial value for W. I'll go with my learning rate of 0.01. So this is my alpha. And then here's my gradient. And I got my new value for W. And I'll just recurse that 100 times. And I'll eventually get my answer. Now, I can actually plot this. Again, I'm just plotting the loss at every step along this pipeline. And you can see that on the right over here. On the x-axis, I have my number of gradient steps, starting at 1 and going to 100. And then on the y-axis, I have my loss. So my initial loss was slightly greater than 3, and then by the end, my loss is certainly less than 0.5. I like this plot because it's showing that over time, my gradient descent is in fact finding values of W that decrease my loss, which they should. It's also showing me that I'm converging, right? I found some values of W and I don't think I can improve any more than what I have. Like the values of W I found are minimizing that loss as much as I can, given what, the data I've been provided. Okay, so in summary, gradient descent, it's an optimization approach that learns parameters W in order to minimize some loss function like what we just saw. The advantage is that this can be used to a wide variety of different settings, so it's got a very general application. Although linear regression has got a closed form solution that we found in the last lecture, you can use gradient descent for linear regression and for other contexts. For example, when we're training neural networks, we often use different variants of gradient descent in order to update the weights of those neural networks. One downside is that instead of converging to the global minima, gradient descent could get stuck in a local minima. And I'm visualizing that on the right. So this is the same sort of plot we had before, where I've got my weight vector with two different elements, W1, W2, and I'm plotting those weights. Here is my initial guess for W, and this was unfortunately a very bad initial guess, because when I use gradient descent, I go down my gradient, I end up right here. Now this is a local minima. If I look just locally in this area, it seems like the best solution. But if I zoom out and look at the entire contours, I realize actually I could have minimized my loss better over here. So gradient descent, because it's taking these local gradient steps, it could get stuck in a local minima instead of finding the global best solution. So that's one downside to this algorithm. Okay, so in today's lecture, we talked about how learning connects to optimization, and we introduced the gradient descent approach. If you'd like to test this for yourself and also go through some code, I encourage you to go through the practice set. You can find this in the description or the pinned comment. The first page has the questions and the following pages have their answers. Once you've practiced a little bit, I encourage you to move on to our next lecture. And in this next lecture, what I want to do is I want to apply gradient descent in a different context as I'm trying to learn my robots control gains. So I look forward to seeing you there.